Hello, grade 11s. I hope that you've had a good week. First week back at school. I hope that the circuits section is making sense and that you are getting to terms with understanding how to calculate all the different things. I'm going to start off by just going over the corrections for question 13 and 14, and then we'll start on the new topic for today. Okay, so starting with question 13, it says the graphs below show the relation between current and potential difference for a resistor and a lamp. Okay, so what I would recommend that you do here is to just take your highlighter and just highlight the two different graphs just so that it's a little bit easier for you to pick up on the relationship between the two. So the resistor is the one that is a straight line and the lamp is the one that is doing the curve. Okay, so it says, first question, describe how, if at all, the resistance varies as the current increases in the resistor or in and the lamp. Okay, so let's have a look. When I look at the resistor, it says what happens to the resistance as the current is increasing. So the current is increasing going this way. So as I'm moving along the graph, I can see that in both cases where the voltage is getting larger, the current is increasing. So with the resistor, I can see that the resistance, which would represent the gradient of the graph, I can see that the resistance is going to remain constant. Okay, so we can say that the resistance remains constant as the relationship of 1 over V is constant. Okay, so you can conclude that the resistor is ohmic. Okay, remember that resistance is equal to V over I. Okay, but in this case, if we look, the delta Y over delta X is I over V. So with this particular case, right, it's been reversed. So if you think about it, that these two are inverses of one another, which means that I over V is actually 1 over R. Okay, so if we are specifically trying to figure out, okay, it still helps us to see the resistance, but it's the relationship of 1 over V, which is constant. Okay, so just to be aware of that. So with the lamp, you can see that the resistance is changing. Okay, what's happening is that the graph is curving like this, which means that that 1 over R relationship is increasing. So if it was just R, then it would look different, the graph. In this case, it's 1 over R and not just R. So all you're asked to do is just interpret the graph. So it says the resistance increases for the lamp as the relationship of 1 over V is not constant. Okay, we're looking at how the resistance is changing over time. So the resistor here is non-ohmic. Then it says, state the values of the potential difference and the current when the resistor and the lamp have the same resistance. Okay, so we look at this graph and we see, okay, where is it that they would have the same resistance? It would be at the point where they are intersecting. So they intersect at that point over there. So what you need to do is, if this is a test, in order to show me where you're getting the values from, you must indicate on the graph where you're getting this from. And you do this by showing on your graph how you are reading it. So you can see that I go to the side and to the bottom to see, okay, well, I can see that the current is going to be 4.5, and I can see that the voltage is going to be 7. So the current is 4.5 amps and the potential difference is 7.0 volts. Okay, moving on. So it says determine the resistance of the resistor. So now it's important to take note, like I said earlier, that the gradient here is not equal to the resistance but the inverse of resistance. So this gradient, which is equal to delta I over delta V, is going to be the inverse of resistance, or 1 over R. So you can still continue with it. So we'll choose points on the graph. So we will take the change in, so we'll start, our first point we'll take is 0 and 0. So I'll call that point A. And then the other point that you're going to take is going to be, this is for the resistance, so we're going to take the resistor. So you can choose any point on the graph. I'm going to take where the current is 5.2 and the voltage is 8. Okay, just make sure that you give yourself a good spread. Okay, so these are the 2 points that I'm taking specifically. So you just take any 2 points on the graph and you should still get to the same answer. So I'm going to say 5.2 minus 0 over 8 minus 0, which is going to be equal to 0.65. But now it's important to remember that this is the inverse of R. So that means that this value here, or rather we should say it's 1 over R. So you need to swap these values around in order to get the actual resistance, which is going to be 1,54 ohms. So on your calculator, this answer, it will be given to you as a fraction. You'll take the 2 and you'll swap it around, or you can take your answer and make it an inverse. Okay. That's how you'll get the answer. So you'll take this answer here and you'll inverse it. Okay, next is, it says learners use Ohm's law to determine which one of the two resistors, A or B, has the greater resistance. For each resistor, they measure the current through the resistor for different potential differences across its ends. The graph below shows the results obtained in the investigation. Okay, so it says the learners are supplied with the following apparatus: 6-volt battery, voltmeter, ammeter, rheostat. A rheostat is just a variable resistor. So it's basically like a dimmer. So you can basically change the resistance. The conducting wires. It says draw a circuit to show how the learners must use the apparatus to obtain each of the following graphs. So they are trying to use Ohm's law to determine one of the two resistors, A or B, has the greater resistance. So they measure the current through the resistor for different potential differences across the ends of that resistor. So what we have is, we have the cell, and then I'm going to have an ammeter and a resistor. And now that resistor is going to have a voltmeter attached to it. So I just want to neaten up a little bit. So there's a resistor, and there is, we'll call it R, and then there's a voltmeter. Okay, it doesn't matter which direction your voltmeter goes in. And then remember that they add a variable resistor as well, a rheostat. So that just looks like a normal resistor with an arrow through it. And then it will end. Okay, that's everything that we need. Remember, take note that you have every single thing that you're going to put. So obviously the resistors A and B are going to be here. Okay, it's not two resistors in one circuit. They replace the resistor R with A and B. Write down one variable that must be kept constant during this investigation: temperature. Okay, remember, otherwise if temperature changes, the resistance changes. Then it says which one of A or B has the higher resistance, and to explain your answer. Okay, so the higher resistance, if you think about this now, you might say, okay, well, resistance is the gradient, so clearly this one must be higher because it is the higher gradient. But remember that this is current over potential difference, which is the inverse of R. So it is not the gradient for R, but rather it is the gradient for the inverse of R. So that's very important. So now basically we are trying to find where the gradient is the steepest, or the lower gradient, because the lower gradient, if you think about that, right, the lower gradient is going to have the higher resistance, because it will be the same, like 1/2 and 1/4. Okay, that when you inverse it will be 2 and then 4. So obviously this one that appears smaller in gradient will have the larger resistance, because if you inverse these you will get a bigger answer with the smaller fraction. Okay, so the actual answer then is B. So the reason why it's B is because the ratio I over V, or the gradient, is smaller. So basically that means that the resistance is greater. Okay, so remember, at all points we are trying to figure out this I over V relationship, okay, which is different to V over I. Okay, so just take note of when we are working with the one or the other. Okay, so you can rule off, you can write today's date. It will be the 9th of May. And now we're going to start a brand new topic in circuits that you might not have covered before, but this is essentially where the grade 11 circuits begin. Okay, so we're going to look at power and energy. Okay, so remember we said that when you have an electrical circuit, that there is a movement of electrons. So when these electrons move through a resistor, it is going to need electrical energy. And that energy is normally converted into another form of energy, other forms of energy, such as heat or light, depending on if it's like a light bulb or just any normal resistor. So it's mostly heat, but it can do other things such as light or even mechanical sound. So you're looking at a variety of different energies that can be converted from that electrical energy. Okay, so when that energy is converted, remember we've already discussed how energy relates to the work done and how work done per unit charge is voltage. So when we think about the change in energy or the conversion in energy, with the symbol delta E, we say that that is equal to the work done. Okay, so when we refer to work done, it means that we are looking at how energy is being converted. This is something that you should already be quite familiar with. So work done has the symbol W and it is measured in joules. Okay, so that's how we start off this topic, by understanding what does it mean when we have electrons that need to push through a resistor. Okay, in order for them to push through the resistor, there has to be this energy that is required. And that work done now relates to the new topic that we're going to discuss today, which is power. So if you look at your SAGS document, power is the second part of this electric circuits. Now there are no definitions in this portion, so you don't have to necessarily define power, but you must be able to use the equations correctly. So, and you must understand what it is. So power is basically the rate of electrical energy conversion. Electrical energy conversion. So we are looking at how the time it takes in order for that energy to be transformed into something else. So mathematically, we would say, well, then the power would equal to the energy conversion over a change in time, or in other words, it would be equal to the work over time. So we have this equation here where P is for power, which is measured in watts. You have work or energy measured in joules, and you have the time measured in seconds. Okay, I'm just going to make a little note here that this W here is watts and that W here is for work. So just be careful, make sure you know what we are actually looking at, what the differences are here. Okay, so now if we think about how all of this starts to relate together. Okay, we've already discussed a work charge formula. So you must also understand that the power that a device is going to dissipate is equal to the product of that potential difference and current. So basically, power is equal to the product of potential difference and current, meaning that you could write the formula PIV, P is equal to IV, where P is power, I is for current, and V is for potential difference, measured in volts, amps, and watts. Now from this equation, we can derive certain formulas from this power equation. So if we start off, we can think, okay, well, power is equal to W over delta T. Now if I consider my other equations, so we'll just leave this one here. I want to look at the three equations that we've done already. So we've done Ohm's law, which says that V is equal to I times R. We've done I, which is equal to Q over delta T, and we've done V, which is equal to W over Q. So if we consider this now, we can say, well, according to this equation, we could derive further equations from what we've already found. So if we think about taking, let's say, something like the W, we could say W is equal to V times Q. But we also know that V, well, let's take this one here. We can replace Q, and we can say, well, we know that Q is equal to I times delta T. So the work would equal to V times I times delta T. Okay, the W. That would obviously then be the work. So it's just a way that we can get to a work equation. Okay, we could further elaborate on this, and we could actually say, well, using Ohm's law, we could say, well, V is also equal to I times R. So we could even say that W is equal to I times R times I delta T, which is I squared R delta T. So now when we start, we could do the same thing where instead of replacing V, we could replace I. So we could say V times now I is equal to V over R. So we could say V over R delta T. So W is equal to V squared over R delta T. So now these equations are basically used in order to help us figure out more of these power equations. So we technically, from this, have four equations for W. We can say, well, W is equal to P delta T. We could say W is equal to V I delta T. We could say W is equal to I squared R delta T, or W is equal to V squared over R delta T. So it's just four ways that you can actually get to these formulas by using what we already know, Ohm's law and all the other stuff. Okay, but if we think about power itself. Okay, power is now related back to this W over delta T. So if we had to take all of these other work equations and put it into the power, then we'll notice how it's going to change. So let's have a look at this one here. Notice that if you said W is equal to VI delta T, if you divided both sides by delta T, you would have W over delta T is equal to VI, which we've already established power is equal to W over delta T. So that's where that P is equal to I times V comes from. This one that we did here, just to show you where it's coming from. So all of this is just showing you where all of these equations are coming from. Okay, you don't necessarily have to know it, but remember, with those multiple choice questions and those relationships, it's very important that you're able to actually derive where all of these things are coming from. Okay, and then furthermore, using Ohm's law, we can also continue to add on to this with resistance, because now we can say, okay, well, how would resistance relate here? So we can say, well, because resistance is equal to, well, let's do in terms of V and in terms of I. So V would equal to I times R, and I would equal to V over R. So I could take these two and put it in to the power formula. So I could say, well, power could equal to, if I replace V, it would be I times R, which is I squared R. And I could go one step further and I could say, oh, but I could also say that P is equal to, and replace I with V over R times V, which is going to be equal to V squared over R. Okay, so just so that you can see that there are quite a few different ways that you can calculate it, which is why there's quite a few power equations that you can use. So now if we look at our power equations, we can say, well, we now have four power equations. We have power is equal to the work over delta T. We have power is equal to I times V. We have the power is equal to I squared times R. And we know that power is equal to V squared over R. Okay, like I said, you don't necessarily have to know exactly where they come from. It's just to show you that these equations actually aren't anything new. We just keep, it's not four different equations. It's just equations that we are building onto one another the entire time. Okay, so let's do some example questions. So exercise 24, I believe it is on page 129. So it says a 7-watt LED light bulb is used for 3 hours. How many joules of energy is converted? So they give you 7 watts, which is the power, and they tell you 3 hours, which is time. They want to know energy, electrical energy converted. So that's work, which is equal to P delta T. Now the power is 7, but the time is 3 multiplied by 60, multiplied by 60 again, because you have to convert from hours to seconds. So the answer is 75,600 joules. Okay, make sure that you convert. Okay, that's the most important thing here. Convert. Okay, let's look at number 2. It says a 400-watt lamp, so they said 40 watts is power, is turned on for 1 hour. So there's time and it's an hour, so you have to convert it. How many joules of electrical energy is used? Again, W is equal to P delta T. You should take a moment to pause the video and to also try these questions on your own before, instead of just copying down the answers as I'm doing it, okay? So make sure that you're interacting with this. Okay, so take a moment for number 3. I'll just explain that this GJ is for gigajoules. Now gigajoules is 5 times 10 to the 9 joules. Okay, so take a moment and try and answer this question. It says the motor uses 5 gigajoules of energy over the course of a day. A day would be 24 hours. How much power is used? So power is equal to energy over time. Now the energy is 5 times 10 to the 9 divided by 24 times 60 hours, 60 minutes times 60 seconds. So you take the hours and convert it. So you put the whole thing in your calculator and you would get 57,870.37 watts. Okay, if we look at number 4, it says 750 watts, so that's power, uses 150,000 joules work. How long in minutes was the lawnmower used for? So we're calculating time. So let's see, T is equal to W over P. So it's 150,000 divided by 750, which is equal to 200. But this is seconds, so we need to convert to minutes. So to go from seconds to minutes, you need to divide by 16. So we're going to say, therefore it's 200 divided by 60, which is equal to 3,33 minutes. Okay, if we look at number 5, it says a computer runs on a battery of 5 volts, so you're given voltage, with a current of 0.75 amps. Calculate the power. Nice and easy, we're just going to use PIV. So we have 5 times 0.75, which is equal to 3.75 watts. Okay, number 6. A DC generator has an EMF of 200 volts and provides a current of 1.5 amps. Okay, so pause, answer how much does it generate, how much energy does it produce each minute. So take a moment, pause, and try and do it. So in order to calculate power, you can see we're going to use just PIV, which is 200 times 1.5, which is 300 watts. Then it says how much energy is produced each minute. So W is equal to PT. The power is 300 and 1 minute is 60 seconds. So that's going to be 18,000 joules per minute. Okay, so as for the rest of the questions, I'm going to ask you to complete them for homework. So I'm going to give you from question 7 to question 14. So you can see that it doesn't take very long to answer these questions. They're very straightforward, just like a plug and play kind of formula. So practice this and then we'll start going over some of the more complex calculations in the next lesson. Okay, so basically, just to recap once more, that power is about the rate of energy conversion, where energy is the work. So the power is equal to W over delta T. But now you can remember that power is equal to I multiplied by V, but all of that comes from the energy conversion calculations and from Ohm's law. So all of these equations, the 4 equations for power and the 4 equations for work, all come from using Ohm's law and just substituting it in. But if you know the two most important formulas is P is equal to the rate of energy conversion, and that power is the product of current and potential difference. Okay, so if you look at your formula sheet, you'll find that all of these calculations are there, all of these formulas. So if you go to electric circuits, you'll see that there are 3 equations for work, the 4 equations for work and 4 equations for power, all given under electric circuits. Okay, so make sure you use a formula sheet when you're answering these questions. And that's it. So good luck. I hope that you have a good weekend, and I will then see you on the next one. Okay, bye bye.